Assalamualaikum and good day. This is the lecture for BMFG 1213 Engineering Materials. My name is Dr. Muhammad Shahdan bin Muhammad Swan. I will continue on chapter 12B, Functional Properties of Material, Magnetic Properties of Materials. This chapter will cover the CLO2, which is analyze the properties of engineering materials based on its structure, which is included in the Bloom taxonomy analysis. Outlines of this chapter are: first, we will learn about the basic concept of magnetic properties. Then we will be introduced about the diamagnetism, paramagnetism, and ferromagnetism. Furthermore, about the antiferromagnetism and also ferrimagnetism. And finally, this chapter will cover the soft and hard magnetic materials. So at the end of this chapter, you should be able to determine the magnetization of some materials, explain diamagnetism, paramagnetism, and ferromagnetism, and finally you should be able to describe magnetic hysteresis, or we call it pH curve. Magnetic properties of metals. What really happens when we apply the magnetic field to the metal? We take the iron as example. This figure shows the photomicrograph of single crystal of iron. We can see there are few of domains, magnetic domains exist in the iron, but with different uh, dipole moment direction at H equal to 0 or no magnetic field. When we apply the magnetic field into this direction, the domain with the dipole moment with the same direction to the H will start to grow, and when we apply for the H at the same direction, the domain with the same direction dipole moment will enlarge, and this process will continue until all the domain are following the direction of the magnetic field. Basic concepts of magnetic properties. Magnetic force generated by moving electrically charged particles. Forces can be represented by imaginary lines grouped as fields according to right-hand rule. So this is the magnetic field line of force around the wire loop, current wire loop, and a bar magnet. We can see for the current wire loop, if we apply the electric uh, current in this loop at this direction by using the right hand rule, we can have the direction of magnetic field downwards through this loop. And for the bar magnet, the material has magnetic dipoles, which is north and also the south pole. The magnetic field will move from the north and it will enter the south. So the magnetic field is represented by the red arrowed line. Magnetic dipoles can be found in magnetic materials. Can be thought as small bar magnets composed of north and south poles. It is influenced by magnetic field, tend to orient themselves with field. Magnetic field vectors. Externally applied magnetic field equal to magnetic field strength, or H. If H is generated by cylindrical coil, as known as solenoid, consisting N closely spaced turns, the magnetic field strength can be calculated by using this formula, where H equal to Ni over L. L is the length of the solenoid, I is the applied current, and also N is the number of the turns. Unit of magnetic field strength is amperes per meter or ampere turns per meter. This one ampere per meter or ampere turns per meter. The second magnetic properties of the metals is magnetic induction. The magnetic induction can be determined by measuring the magnetic flux density B. Represents the internal field strength within a substance subjected to a magnetic field, and the unit for magnetic flux density is Tesla or Webers per square meter. For the solenoid, we can find the magnetic flux density by using this formula B naught equal to mu naught H, where the mu naught is the vacuum permeability and the H is the magnetic field strength. While for the solenoid, which contain or have the iron bar at the center, we will use this kind of formula where magnetic flux density B equal to mu naught H plus mu naught M. We add this mu naught M because of the magnetic induction by magnetized iron bar at the center of solenoid. So the iron bar is magnetized by H. Then we can get the overall formula is B equal to mu H, where the mu is the permeability, overall permeability, while M in here we can calculate by using this formula. Magnetization of solid equal to Chi M H, where M is proportional to the applied magnetic field H, and the Chi in here we can calculate by using this formula mu R minus 1, where the mu R is the mu over mu naught, or the mu of the solid over the mu in or the vacuum permeability. Origins of magnetic moments. To know in detail about the origins of magnetic moments, we must respond to quantum mechanics law. The electron's magnetic moment is not due to a current loop, but it is instead an intrinsic property of the electron. Two main contributions. The first one, an orbiting electron, orbital magnetic moment, and B, electron spin. Due to incomplete cancellation of electron spin and or orbital magnetic moments as consequence of the electron structure. So this must related to the electron structure because of the incomplete cancellation of either by the electron spin or the orbital magnetic moments. Then the incomplete will result in a change of electron structure, then will cause the magnetic moments. Their magnetism and paramagnetism. The material that shows the diamagnetism properties, we call it the diamagnetic material. The diamagnetism, the very weak form of magnetism found in all materials, is non-permanent, persists only with applied external field. In the presence of a field, dipoles are induced and align opposite to the field direction. Magnitude of induced moment are extremely small, where the mu are slightly less than the unity. Magnetic susceptibility is negative in the order of negative 10 to the power of minus 5, where B is less than in vacuum. So this kind of property is found in all material. Without the applied magnetic field, there is no dipole. But when we apply the magnetic field it will induce the dipole moment in uh, the domain. But this kind of phenomena is non-permanent. It will change back to its original condition when we remove the hash. So when the hash back to zero, it will not have the dipole moment. Next is paramagnetism, where the material that shows this kind of properties, we call it the paramagnetic material. In paramagnetic material, atom has permanent dipole moment. In the absence of H, random moments orientation, no magnetization, the presence of a field, atomic dipole frequently aligned by rotation with H. Dipoles act individually with no mutual interaction. So for the paramagnetic material is already have a dipole moment although at the zero magnetic field. When we apply the magnetic field, the moment will start to align by following the direction of magnetic field. And the dipoles act individually with no mutual interaction. This figure shows the flux density B versus the magnetic field strength H for the magnetic and paramagnetic materials. If we observe this figure, we can find that the magnetic have very low flux density compared to the paramagnetic, all at the same H in here, at the same magnetic field in here. So this is due to the uh, relatively small of permeability of the diamagnetic material compared to the paramagnetic material. This table shows the room temperature magnetic susceptibilities for diamagnetic and paramagnetic materials. We can see in here for the diamagnetic material, it has the negative susceptibilities compared to para all have the positive susceptibilities. So when the magnetic field is applied to this kind of material, it will oppose the magnetic field, while for paramagnetic material, it will follow the direction of magnetic field. Ferromagnetism. Certain metallic materials have this kind of properties, which is the ferromagnetism. Is permanent magnetic moments and mutual alignment of atomic dipoles, although in the absence of magnetic field H, results from uncancelled electron spin and orbital magnetic moments. Coupling interaction forces magnetic moments of adjacent atoms to align with one another, or we call it magnetic spin. Coupling forces arise from the electronic structure of the metal, manifest very large and permanent magnetization M. The transition metals such as iron, BCC ferrite, cobalt, nickel, gadolinium have this kind of properties. In the formula to calculate the flux density, we are using this kind of formula B equal to mu naught H plus mu naught M. But for ferromagnetic material, the M is very large, so that we can ignore this mu naught H. Uh, so we can have this kind of formula B is around mu naught M or equal to mu naught M, since the mu naught H is not significant compared to the very large magnetization of ferromagnetic materials. Maximum magnetization or saturation magnetization MS, all magnetic dipoles in solid mutually aligned with H correspond to saturation flux density B. Bs equal to m atom multiplied by n atoms, average moment per atom times density of atoms, while m atom 2.22 mu b and 1.72 mu b, 0.620 mu b for iron, cobalt, nickel respectively. For iron 2.2, cobalt is 1.72, nickel is 0.6. So this is the domain for ferromagnetic material. In the absence of magnetic field, H equal to 0, the dipole moment already aligned, although in the absence of the magnetic field strength. And once the H is applied direction, it becomes the alignment and the dipole moment becomes greater by following the direction of H. Antiferromagnetism and ferrimagnetism. Antiferromagnetism experienced by materials that are not ferromagnetic. Alignment of the spin moments of neighboring atoms or ions in exactly opposite direction, for example, manganese oxide. No net magnetic moment for oxygen ions. Total cancellation of both spin and orbital moment. For mangan ions, it possesses a net magnetic moment. Moment of adjacent ions are antiparallel, so opposing magnetic moments cancel one another, so no net magnetic moment. For this kind of material, the magnetic moment of mangan oxide, for example, mangan have both direction of dipole moment, upward and downward. It will cancel out each other. And for the oxygen, it's already the total cancellation of both spin and orbital moment. So for this kind of material, there is no uh, call, no magnetic moment for this material, so it will oppose the magnetic field or applied magnetic field. But at above zero temperature or absolute zero temperature, they become para because the thermal energy becomes large enough to destroy the microscopic magnetic ordering within the material. So the thermal energy will destroy all this kind of arrangement, so that it will become para. So for mangan oxide, it will only become antiferromagnetic at 0 Kelvin or 0 temperature. It's similar to the this kind of material, which is a YBCO or LBCO or superconductor material, which have antiferromagnetism, where it will oppose the magnetic field, applied magnetic field. So no magnetic field can be induced into this kind of material, and no dipole moment are arranged in this kind of material. Ferrimagnetism. Some ceramics exhibit permanent magnetization termed ferrimagnetism, different with ferromagnetism in the source of net magnetic moments. Principles illustrated by cubic ferrites. Chemical formula of MFE2O4. In Fe3O4, ions exist in both +2 and +3 ions, has different spin magnetic moment configuration, exists antiparallel spin coupling interaction. Above the critical temperature becomes paramagnetic. Tc in here is the temperature at which certain materials lose their permanent magnetic properties to be replaced by induced magnetism. So it will be easier if we can, or we take a look at this figure in here, the difference between the ferro, ferry, and antiferro. For the ferro, all the dipole moment in that material is in one direction. Okay, all is in one direction. But for antiferro, the direction will cancel each other. The upward will cancel the downward direction, and so there is no dipole moment for antiferro. But for ferromagnetism, the condition where there is dipole moment achieved at T below than Tc, where maybe certain of the dipole moment can be cancelled, but the remaining still have the magnetic properties in them. So for the ferromagnetism, it always occurs in the metals or requires free electrons in the conduction band. So ferro will occur only in metal, but for ferri and antiferro will only occur in insulators, for metals or metals uh, and metal oxide. Okay. The distribution of spin magnetic moments for Fe2 plus and Fe3 plus ions in a unit cell of Fe3O4. If we can see in here, the Fe3 plus cation have 8 dipole moment on the in the octahedral lattice side, upward dipole moment, and 8 downward dipole moment at the tetrahedral lattice side. So each of these dipole moments will cancel each other and it will be complete cancellation. So no net magnetic moment. But for Fe2 plus, the dipole moment was developed at the octahedral lattice side, but at the tetrahedral lattice side there is no dipole moment, so it will remain as the 8 dipole moment upward to sustain the magnetic moment of the Fe3O4. This one is for ferromagnetic material. This figure shows the magnetic susceptibility of different elements in the periodic table. The diamagnetic material is represented by the blue box, the paramagnetic by the gray box, and the ferromagnetic material represented as the black box. The influence of temperature on magnetic behavior. By raising the temperature, it will increase the magnitude of thermal vibrations. Atomic magnetic moments free to rotate, while increase in temperature also tend to randomize the directions of moments that may align. So in ferro, ferri, and antiferromagnetic, the atomic thermal motions counteract the coupling force and cause misalignment. It will result in decrease of the saturation magnetization, or MS, or MS will be zero at Tc, where the Tc varies for material. For example, the Tc for iron is around 768 degrees C, cobalt 1120 degrees C, nickel 335 degrees C, and Fe3O4 585 degrees C. The Tc in here is Curie temperature, and the Tn is near temperature, where the antiferromagnetic become paramagnetic temperature. As we can see in this graph, when we increase the temperature, the saturation magnetization will decrease in here. So by increased temperature will result in decrease in saturation magnetization. Domains and hysteresis. All ferro and ferrimagnetic materials consist of domains, small volume regions with mutual alignment of magnetic dipole moments. Each domain is magnetized to its saturation magnetization. Within each domain, all dipoles are aligned, whereas the direction of alignment varies from one domain to another. Each domain is separated by domain boundaries or walls, where it will gradually change in magnetic dipole orientation across a domain wall. Domains are microscopic, and in polycrystalline, each grain may consist of more than a domain. If we look at this figure, there are three domains. The first domain is the dipole moment is upward. The second domain, the dipole moment is to the right, and the third domain, the dipole moment is downward. The each domain is separated by a wall in here, separated by a wall where in the wall the gradual change of magnetic dipole moment can occur, hence it will change their direction. Flux density B versus magnetic field strength H. In ferromagnets and ferrimagnets, B is not proportional with H. If ferromagnetic or ferrimagnetic material initially unmagnetized start at origin of BH curve, then the slope of BH curve at origin will be mu I, or initial permeability. As H increase, B slowly increase, then rapidly and finally leveling off, becoming independent of H, where it achieved the maximum B or the saturation magnetization. Domain change configuration, shape and size during several stages of magnetization due to the movement of domain boundaries. The at initial domains are random, then it will oriented in direction favorable to applied field, and as many of those are unfavorable, then the process will stop at saturation point when all domains align with H field at saturation flux density Bs. Okay, we look at this figure. We start at the origin where H is 0. When we apply the magnetic field strength H, the flux density also will increase by the mu I, or the initial permeability. Then when we further apply the magnetic field strength, the flux density will rapidly increase until the certain level where it achieve the BS or MS. The BS is flux density saturation, or the MS, the magnetization saturation. For the domain, at the origin, the domain is randomly oriented. So once we start apply the magnetic field, the favorable or direction will start to grow, and the shape also will start to change. Then the most favorable direction will start to grow and grow until all the domains align to the direction of H. So this uh, was achieved at the BS or the MS. Hysteresis: ferromagnetic material subjected to forward and reverse saturation. When H field is reduced by reversal of field direction, the B field lags behind the H because it decreases at lower rate. At H equal to 0, B equal to plus BR, or remnant flux density. Axis of residual flux density material remains magnetized without H. Due to resistance to movement of domain walls at H equal to 0, some net fraction of domains in former direction. So, in the previous slide, we already applied the initial magnetization and it achieved the saturation in here. Then we apply the reverse magnetic field to decrease back the flux density into 0. But when the H achieves 0, the flux density does not achieve 0. It has some value in here. We call it the remnant flux density, or plus BR. And to reduce the B to 0, H field of magnitude Hc must be applied at opposite direction, called coercivity or coercive force. Continue applying H at this direction, achieve saturation at S. Second, reversal to the point S, complete the symmetrical hysteresis loop, yield negative remnants, negative BR, and positive coercivity plus Hc. So when we further apply the Hc or coercive or negative magnetic field, we can reduce the flux density back to 0. So at this point, we call it the coercive magnetic field or coercive point. Or when we further apply the Hc or the opposite Hc, we can have the second saturation in here, and then we reduce back the flux density. uh, we can have the remnants negative flux density at the H is equal 0, and we further apply the magnetic field back, so the flux density can return to its 0 value in here, where we find the plus Hc. So the combination of this process will make or will result in the hysteresis loop. So this loop in here, what we call the hysteresis loop. Comparison between magnetic versus non-magnetic. If we can see in this figure, for ferromagnetic and ferrimagnetic, the pattern are obviously different from the diamagnetic and paramagnetic pattern. For ferro and ferri, if we increase the H, the flux density will firstly increase by initial permeability and then rapidly increase up to the saturation level, where it achieves the Bs and also or the Ms. While for diamagnetic and paramagnetic, the pattern or the increment is proportional. So we can say that the H is directly proportional, uh, or the B is directly proportional with the H. Soft and hard magnetic materials. These characteristics are determined by the area within a loop. Magnetic energy loss per volume of material per magnetization or demagnetization. Energy loss manifests as heat generated within the magnetic specimen could increase the T. Both ferromagnetic and ferrimagnetic materials are classified as either soft or hard on the basis of their hysteresis characteristics, size, and shape. For the soft, magnetic materials are used in devices that are subjected to alternating magnetic field and in which energy loss must be low. One familiar example consists of transformer cores. The relative area within the hysteresis loop must be small. So this one is for the soft magnetic material which have the small hysteresis loop. Uh, it is characteristically thin and narrow, must have a high initial permeability and low conductivity. So this one is the loop is narrow and have high permeability and low conductivity. A material possessing these properties may reach its saturation magnetization with relatively low applied, easily magnetized and demagnetized, and has low hysteresis energy loss. So for this kind of hysteresis loop, it will easily magnetize and demagnetize. Hard magnetic materials. Hard magnetic materials are utilized in permanent magnets which must have a high resistance to demagnetization. In terms of hysteresis behavior, a hard magnetic material has a high remanence, high conductivity, and high saturation flux density, as well as a low initial permeability and high hysteresis energy loss. The two most important characteristics relative to application of this material are the conductivity and what is termed the energy product or stored energy in magnet, designated as BH The value of the energy product is representative of the energy required to demagnetize a permanent magnet. The larger the harder is the material in terms of its magnetic characteristic. So for the magnetic characteristic is known as to have the larger hysteresis loop in here. Hard magnetic materials fall within two main categories, the conventional and high energy. The difference between these two type of hard magnetic materials are the pH values of the conventional is between the 2 and 80 kilojoule per meter cube, and for the high energy hard materials, magnetic material, the energy is must exceed the 80 kilojoule per meter cube. The conventional hard magnetic materials, for example, the copper nickel iron alloys, aluminum nickel cobalt alloys, and also hexagonal ferrites. And for high energy hard magnetic materials, the product, for example, the samarium cobalt magnets and neodymium iron boron magnets. So we have come to the summary of this chapter. The first one, a magnetic field H can be produced by putting a current through a coil. Then the magnetic induction or magnetic flux density B occurs when a material is subjected to a magnetic field and changing the magnetic moment. Types of material respond to a field are ferric and ferromagnetic, which shows the large magnetic induction. Paramagnetic is poor magnetic induction, while for diamagnetic, opposing the magnetic moment. There are two types of magnet. The first one is hard magnet, which have the large conductivity or the wide hysteresis loop, while the second one is soft magnet, have small conductivity and narrow hysteresis loop. That's all for this chapter. Thank you for your time. Thank you.